particular also a lot of our ASG members joining from their respective countries. And it's a great pleasure to run the IBS colloquium, IBS Physics colloquium at Daejeon today with our speaker, Professor Ora Entin-Wohlman, who is also part of the ASG, which advanced study group, which has been active in various forms at our center, and which is actually even now continuing activities in an online form. And we hope very much that in the future these activities will be again physically visible at our center. So let me say a few words about Professor Entin-Wohlman. She did her master at the Technion in Haifa, and then got her PhD from Bar-Ilan University in '73. And then she had various positions at Tel Aviv University and at Ben Gurion University. And in addition was visiting a visiting professor at a number of other universities in Israel, but also at the University of Paris, at the Institute of Advanced Studies in Norway, Johns Hopkins University, Tokyo University, University of British Columbia, then other institutes for advanced studies in Natal, in Seoul, which is here in Korea, in Beijing and Jerusalem, about again back to Israel, but also at Argonne National Lab and NIST. So quite an impressive list. And currently she is a professor emeritus at Tel Aviv University. Published lots of papers, has therefore also, not therefore, but has a lot of citations and is well known in the communities which work in condensed matter physics, in particular in superconductivity, magnetism, spintronics, and nanoscience. Ora received the Landau Prize, which is a prize given in Israel. I'm not sure by which body, and the Meitner-Humboldt Prize. I assume that this is given by the Humboldt Foundation. Mm-hmm. Ora, correct me if I'm wrong.
Yeah, this is correct.
Right, and she's a fellow of several physical societies, but what is most important is that she will talk today to us about spin-orbit interactions and topological phase factors. And we look very much forward to an exciting talk. Ora, the floor is yours, please.
Thank you, Sergey, and thank you for the nice introduction. And in the meantime, you've seen the picture of my university, Tel Aviv University. So let me tell you that this is the first time I am giving a talk on Zoom. And therefore, I went into the internet to see how should one give a talk. And the advices given there were tell a story, which is easy, be qualitative, use simple physical pictures and graphs, keep formulae simple, that's also easy. But then came the harder part, like understand everything you present, which is not that easy. Engage the audience by moving around or keeping an eye contact, which I cannot do. And the last one was make the audience think and not just listen, which indeed I don't know how to do that. So I'll try to do my best. The plan of my talk, which was also advertised, has to do with geometric phases in condensed matter physics, of course. But to give you an example of what I mean, I show here the classical analog of a geometric phase, and that if you move on a sphere, always along I think this longitudinal lines, then when you come back to the point where you started, there is a phase in between the two directions. This is, of course, the geometric phase or the spatial phase. But we want to see what happens in this to this in physics. So I'll start by explaining what is the Berry phase and the Berry connection in condensed matter system. And then I'll go to the paradigm example, which is the Aharonov-Bohm phase and its surprising measurement in condensed matter interferometers. Okay, so let us start. What is a phase? The phases we are talking about are the phases of the wave functions of a condensed matter, and basically the electronic wave function, which is the wave function that we get by solving the Schrödinger equation. Here I wrote the Schrödinger equation in some parameter space, which is denoted by psi. So if you ask yourself, what is the phase difference between two wave functions at two different parameters, psi1 and psi2, you can simply define it as the product of the two functions divided by their absolute value. And this thing has absolutely no physical meaning. So it doesn't say anything. However, if you add the phase difference, when you, I think your picture covered part of my screen, and I don't know how to get rid of them.
Which picture, Ora? I'm not sure what you see.
Your photos. Let me do this.
Okay. You just have to.
Oh, now I see everything. Okay, so I was saying that if you add the phases of the wave function when you take a trip in parameter space, like you go from a point denoted by psi1 to psi2 to psi3, etc., until you come back to yourself, which is denoted here, then this thing, this quantity is gauge invariant, because any transformation that you can do on the phase will disappear by this summing up along a closed curve. And since it is gauge invariant, there is some hope to see it in real life. So when you, instead of going from one point to another in the parameter space, you go to some continuous parameter space and you take a continuous curve, then the differences in phase becomes this quantity, which is the wave function, and the gradient in parameter space of the same wave function with a quantum average. And when you do the integration over the closed curve, you get what is called the Berry phase. And the integrand itself is called the Berry connection. And as you can see, the Berry connection is not gauge invariant, but the Berry phase is. So if it is a gauge invariant, as I said, we can measure it. And the paradigm is of this measurement is the Aharonov-Bohm effect. So let me take it. Let me take you through this effect. Suppose we have an electron in a box which is centered at R. R is going to be our parameter space, and there is no magnetic field. Then we know that the Schrödinger equation is simply given by the kinetic energy plus some scalar potential times the wave function. When we apply a magnetic field, but our box where the electron is still not in the presence of electric field, like if you think about solenoid that produces the magnetic field, we take the electron out, and the only thing that the electron feels is the vector potential that produces the magnetic field. And then, as we all know, we have to add to the momentum the vector potential, and we have to solve this equation. And as we are taught in second year, one can do a gauge transformation on the wave function that is very simple, and we can gauge out the vector potential and come back to a Schrödinger equation without the vector potential. And this this phase that gauge out the vector potential is just the flux accumulated from the magnetic field along a certain path. So we go from one place, we take our box along this line of the vector potential, and we collect a flux, magnetic flux, and the magnetic flux is measured in units of the flux quantum, that's H bar C over E. So we get a dimensionless quantity, and this is called the Aharonov-Bohm phase, which at the time was rather surprising because the electron changes its properties, although it does not move where the magnetic field is. So what is the connection to the Berry phase? In order to see this, we repeat the same calculation, but now we do it as Berry told us to do. Namely, we shift our box, namely we are going in parameter space, which is characterized by this capital R, and we simply put everything into the expression that Berry gave us, and as a result, we find the same property, namely the magnetic flux through the closed path followed by the electron, and this is the Berry phase. So the Aharonov-Bohm phase is a Berry phase of an electron moving in a magnetic field. So the Berry phase is, to summarize this little lecture, the Berry phase is the fractional part of the magnetic flux in units of the flux quantum, and it is gauge invariant, and therefore it is measured. So people wanted to measure it, and this measurement, obviously, you measure a phase by detecting some interference. So what do we understand by interference? Suppose we have a certain electron gun, and the electrons are going through two slits. Then the probability to find a spot on this screen, say, after a long time becomes this oscillatory function, which is the absolute value of the wave function to go through one slit, that's called phi sub 1, and the second slit. So how do we do this with electrons in order to measure the Aharonov-Bohm phase? The answer is in a condensed matter interferometer. So what do we have? We have a source of electrons, and we have a drain where we collect the electrons, and we have the two slits. I will show you in a minute the picture of the actual experiment. And one wave function goes through this path, which is called little a, and the other goes through this path, and there is a magnetic field within the path. So what do we expect? As we were taught in second year, what we have to do is to take the wave function along the path A, which I call here psi A, and the wave function along psi B, add them, take the absolute value squared, and this is what I will see on a screen placed on the drain. Now we know that the wave function in the presence of a magnetic field is the wave function that was there without the magnetic field, times a phase factor that we discussed in the previous slide. So when we do the algebra of adding the two wave function and taking the absolute value to see the intensity, we find that there is an interference term, which is proportional to the absolute values, of course, and then cosine of the Aharonov-Bohm phase, the flux in units of the flux quantum, plus the phase difference of the original wave function. That psi A, in the absence of a magnetic field, has some phase which is called here alpha sub A, and similarly for alpha sub B. And in fact, when people started this interferometry of electrons, what they wanted to measure was this phase of the wave function. Okay, so if we continue, we can see the original experiment that was done in Israel in the group of Moti Eilblum by Amir Yacobi. And what you see here is a source of electrons, S, and a drain, and the two passes, which I mark them by this circle. You see the magnetic field, and you see something which is called plunger gate, and by this plunger gate, you can change the chemical potential or the number of electrons. I will come to this. And then what they measured in the experiment was simply the conductance or the current. And indeed, they saw an oscillatory behavior, as you can see here, and the oscillation period indeed gave us the flux is the area in this notation, gave us the flux in terms of the flux unit. So this looks very, very nice. And people were very happy about this because this proved that the Aharonov-Bohm effects exist. But remember that what they wanted to do is to measure the phase difference between the wave function going this way and the wave function going that way. And then happened something rather interesting. So what they do was to change the gate, the plunger gate. This is the y direction of this figure, and look at the conductance. And you see the conductance is oscillatory. And as you change the plunger or the gate voltage, then you can even double the periodicity. But it is always even in the magnetic field. It is even in the magnetic field, which is the x-axis, which means that they didn't measure the phase of the wave function. How do we see this? Let me go back and remind you what they wanted. They wanted to see oscillatory behavior, which is the magnetic flux, the Aharonov-Bohm flux, plus something else, which should be the phase of the wave function. And lo and behold, they saw only this one, because if the expression is like this, then the result is not even in the magnetic flux because of this term. But in the experiment, as you can see, the conductance was always even in the magnetic flux. So what happens here? That was about in the 80s. Actually, they should not see anything other than what they saw, namely that the conductance is even in the magnetic field. And the reason are the Onsager relations, which tells us that when we have a two-terminal experiment, by two-terminal we mean that electron can go in from one terminal and go out from another. There is no third terminal or fourth terminal where they can come in or go out, which means that all the electrons, ideally speaking, all the electrons that enter the ring are also going out. And in that case, Onsager told us that the conductance must be even in the flux. So you can see all harmonics of the flux divided by the flux unit, but nothing about the phase of the wave function. And in this connection, I would like to tell you a story. I once was in Yale University, and they have a cemetery where Lars Onsager is buried. And this is the tomb, the stone on the tomb. And you can see that he was born in Oslo, Norway. He was a professor of Gibbs professor. He won the Nobel Prize that we know. And there is a little star here, and you go down and say, etc. And it was rather strange. So we asked how come that this rather unique stone, and it turns out that his widow was in some fight against a widow of another well-known physicist. And the other widow, when her husband passed away, had a tombstone with all the curricula vitae on it, whatever he did. So in order to fight that tombstone, she said Nobel Prize and etc. So I find it amusing. Okay, so the conclusion of this part is that because of Onsager relation, which dictate that the longitudinal conductance is even in the magnetic field, the phase of the wave function could not be detected. That's not the experiment to detect the wave function, but it did prove the existence of the Aharonov-Bohm effect. So the two-slit formula that everybody knows to derive does not work for electronic interferometer. And why is this? It's a matter of another colloquium, I think. So what we did so far was to define the Berry phase and the Berry connection in general, and to look at the Aharonov-Bohm phase and its surprising measurement in condensed-matter interferometer. And now I come to the main topic of our research group in the PCS, which has to do with spin-orbit coupling and the topological insulators in the Aharonov-Casher phase. Okay, so what is the spin-orbit? And first, let us ask, why study spin-orbit coupling? The reason to study effect of spin-orbit coupling, this we can take from another Nobel laureate, that's Albert Fehr, who said in 2014 that a novel approach to what he was interested in exploits the spin-orbit interaction in non-magnetic materials that can detect and use spin-polarized currents. And this opens the way to spin devices made of non-magnetic materials. So the emphasis was non-magnetic, and still you can do things with spins that can operate without magnetic field. So that's a good reason to study spin-orbit interaction. And let me remind you very, very briefly about this interaction. So in quantum mechanics, we start from the Dirac Hamiltonian, which I don't present here, and we expand it in powers of 1/c squared, the speed of light squared. And then we get a bunch of terms. This is the usual Schrödinger equation, kinetic energy plus potential energy. Then there is some correction to the kinetic energy. Let me jump to the last term. This is called Darwin term, and it goes like the second derivative of the potential. But then you also create a term, which is the spin S times the gradient of the potential, the vector product with the momentum. And this is the spin-orbit coupling. Why spin-orbit? Because spin is coupled with the orbit, either by this gradient or by the momentum. However, you also notice that this term is multiplied by 1/m squared, c squared, m being the mass of the electron, and c is the speed of light. And therefore, you would assume that this is very, very small. So if the potential is rotationally symmetric, then this gradient times vector product with P gives you the angular momentum L. And here is the spin-orbit interaction, as is well known, S dot L. Okay, so the spin-orbit Hamiltonian for atoms will be some very small coefficients, and S dot the angular momentum. But what happens to electrons in a condensed matter system? For electron in solids, it's better, or it's more useful or more expedient to look at this in a little bit different form. We have, of course, the spin, which I'm going through this talk to denote by the vector of the Pauli matrices, sigma. And there is the momentum, of course, but the gradient of the potential, you can think about it as an electric field. So if you have if the electron moves in a region where the electric field is active, you will have spin-orbit interaction. And because it's due to electric field, it gives the possibility to monitor or to modulate the spin-orbit interaction in the experiment. Okay, so I just remind you, because I'm going to use a lot, sigma. Sigma is the vector of the Pauli matrix. Okay, so for electrons in solids, we have sigma dot E cross P, electric field cross momentum dot the spin. And if you think about this in a minute, you see that this looks like the Zeeman interaction in a magnetic field. The Zeeman interaction is sigma dot B, B being the magnetic field. So there is some effective magnetic field that creates the spin-orbit interaction. And it looks like this. You have the momentum, you have the spin, you have the electric field, and there is a magnetic field, effective magnetic field, that presents the spin-orbit interaction. However, the important point to notice is that the spin-orbit interaction obeys time reversal symmetry, while the Zeeman Hamiltonian does not. And this is a huge difference, a huge difference. So although you can speak about spin-orbit interaction as due to some effective magnetic field, it is not like the Zeeman interaction. Okay. So what is the origin of the electric field that gives rise to spin-orbit interaction? And there are two origins, in fact. There is the intrinsic electric fields, and they arise in solids where inversion symmetry is broken. Then you can have a local electric field and you have a spin-orbit interaction. But as I said before, another source for the electric field is extrinsic. You can do it in the lab by applying an electric field. And this is in particular correct for low-dimensional semiconductor devices, which are now in the forefront of the research. Okay. So let us see what does it mean. So spin-orbit interaction, as I said, obeys time reversal symmetry. What is it means? It means that the energy band for time, I am losing my own. Energy band for time reversal symmetric solid plus inversion symmetry are such that the energy for spin up equals the energy of spin down. So you need two symmetries for this: time reversal, which is the interaction, and inversion symmetry of the crystal that determines the band structure. If you give up the inversion symmetry, if you break it, then what you find, because of time reversal symmetry, is that the energy for wave vector in solids, in band structure is like the momentum. The energy for K, a certain K, certain momentum, and spin up equals the energy of the other direction of the momentum and spin down. This is a result of time reversal symmetry. But it means that for a certain K, for the same K, the energy of up is not equal to the energy of down. Namely, if you break inversion symmetry, you open a gap in the band structure. And this is the origin of this is the intrinsic origin for an electric field and for spin-orbit interaction in solid. An example is the zinc blended. That's a name for the crystal structure, for the unit cell structure of gallium arsenide, where this tiny opening here, you see, I hope you see the different colors, is due to spin-orbit interaction. So this is the intrinsic effect of spin-orbit interaction. Another example, which is very, very famous nowadays, is quantum wells made of I forget the name of this H sub G, and cadmium tellurium quantum wells, where if you put the cadmium tellurium inside two cadmium, I think if you put the HgTe as a sandwich between two cadmium telluride, then you create a band inversion, what is called, due to this spin-orbit interaction. And as a result, you can have a topological insulator, which I am not going to talk about, but the only thing that I want to say about it is that this is an insulator, namely, it does not want to carry current. However, the surface is conducting, and that's the essence of a topological insulator. And they are conducting differently for different spin directions because of the spin-orbit interaction. So this is all that I wanted to say about the intrinsic effect. And now I come to the extrinsic electric field, which is much more important. And from now on, I'm going to talk about the spin-orbit interaction in reduced dimension, basically in 2 dimensions. And there we come to what is known nowadays as the Rashba spin-orbit interaction. So what do we have here? If we have a gallium arsenic plane, and the electric field is normal to the plane, and the plane is very, very, very narrow, we can average over the z direction in the Hamiltonian, and then as a result, we get the Rashba interaction, which is the momentum times the spin operator and cross product with the direction of the electric field. And the electric field and all other parameters enter into something that I call K sub SO, that's the strength of the spin-orbit interaction divided by the effective mass of the electron. So if you look at this expression for the Rashba interaction, and you can play around, you know, you can put the cross here and the dot here, etc. Then you come to the conclusion that it's not much different than the Aharonov-Bohm effect, because like we did in the Aharonov-Bohm effect, we can make a gauge transformation, changing the momentum by this quantity. And then it looks like the Aharonov-Bohm effect. We can gauge it out and find some phase, which is not the Aharonov-Bohm phase, but it is the Aharonov-Casher phase, kind of pseudo-vector potential. So at the end of the day, we'll say that the only effect of spin-orbit interaction in reduced dimension will be to take the wave function and change it by some phase, which is just the spin-orbit interaction with the direction given by the spin direction cross the direction of the electric field. And this looks very, very nice. So we have the Aharonov-Bohm phase, now we have the Aharonov-Casher. However, this thing is a 2x2 matrix. You know, sigma is the Pauli matrices, and the Pauli matrices are two-dimensional matrices. And then the questions come into one's mind. Is it a Berry phase like we have shown in the case of the Aharonov-Bohm phase? And in order not to keep you under stress, I will tell you it is not a Berry phase. And why is this? Because remember, what Berry said is that we have to go in parameter space along a closed contour. So we have to see, we have to see what happens when we go with this two-dimensional phase along a closed contour. But before this, I want to tell you the main advantage of the Rashba interaction. And as I said, you can modulate it externally in the experiment. And this is a very famous experiment done in Japan, where you have a two-dimensional electron gas. This is the green stuff here, two-dimensional electron gas. On top of it, there is what is called gate voltage, which changes the number of electrons in the two-dimensional, the density of electrons in the two-dimensional electron gas. And what these people did was they said they wanted to measure the strength of the spin-orbit interaction. The strength of the spin-orbit interaction is what I call all the time K sub SO, sub-spin orbit. So what they did was to measure what is called the Aspen-Alphen oscillation. The Aspen-Alphen oscillations are measurement of the conductance of this two-dimensional electron gas as function of the magnetic field. And this is an old problem, and it's well known that when you have also spin-orbit interaction, then the oscillation, the Aspen-Alphen oscillation as function of the magnetic field, get some smaller scale oscillations. And from these oscillations, you can deduce the strength of the spin-orbit interaction of that material, independent where it came from. So that's what they did. They measured the Aspen-Alphen oscillation of the magnetoresistance, extracted the strength of the spin-orbit interaction, and plotted it as a function of the gate voltage. And as you can see, the gate voltage, they can change externally in the lab. And as you can see, you can change quite a lot the spin-orbit interaction, which opens the way, you know, for many, many devices. Okay, so now I am back to the question is the Aharonov-Bohm and the Aharonov-Casher effect, are they the same? So what we have by now is the Aharonov-Bohm ring with the phase factor, which is here the charge is Q, which is the flux divided by the flux quantum. And you also have the Aharonov-Casher effect, which is a ring with an electric field and where the spin collects a phase. Okay. So these are the two questions. I mean, the first one is the real question, the physics question. Is the Aharonov-Casher phase a Berry phase? Namely, will it have some physical outcome? And now, since we have the AB effect, which is the Aharonov-Bohm, and we have the AC effect, which is the Aharonov-Casher, why don't we have an AA effect? And I will answer these two questions. So the Aharonov-Casher effect, as I said, is just collecting the pseudo flux from the spin-orbit interaction, but that pseudo flux is a matrix, 2 by 2 matrix. Now see what happens. Suppose we want to go along still not a closed path, but suppose we want to go first along the X direction and then along the Y direction. And collect the phase. And we want to ask ourselves, what will be the end result? What will be the phase that we collected? And the answer is rather interesting. And the reason, I'll tell you the reason in a moment. So when we go along the X-axis, then what is written here is with sigma Y, because we go along X, and we have to take the sigma, which is perpendicular to Z, and this is Y. And then the spin rotates with a little angle, which is this angle. Okay, so sub D times D, D meaning the length that it goes. Then we switch gears, and now we go along Y. When we go along Y, we get here sigma X from this expression. And then the electrons rotate around this direction and collect another phase. The phase is actually the same. But now we ask what happens when you go from here to here? What is the phase? Now comes the main point, because this is non-abelian phase, namely that in simple words, sigma X does not commute with sigma Y, then the end result is rather fascinating. You get a total rotation, which is out of the plane. The electron rotates here in the plane, here it rotates in this plane, and at the end of the day, it rotates around a vector which goes out of the plane. The rotation axis is tilted out of the plane. It does not remain in the plane. Okay, so this is the resultant Aharonov-Casher factor. When we do the calculation...
Laura, I think we have some problems, some weak signal coming from your office. You are frozen right now, right? Maybe, I don't know what.
Should I go back?
Maybe you want to switch off your, I don't know whether it's possible to switch off your video, but keep, of course, the presentation running. But we don't, you're frozen basically.
I can see it, so maybe the problem is in your place.
I don't think so.
I can try to go to another place.
So Amnon, you hear everything?
I hear you, and I see the slides. Everything is fine at my end, and it's mediated via Korea.
I hear you very, very badly as well. So there's some problem.
I also have.
Robert, do you see everything?
No, I have a very damaged sound. Very damaged sound. No,
Is it now better?
It's perfect.
So all the time the sound is damaged.
Now I hear you with an echo.
With an echo.
Double sound.
Here everything is perfect. So
yeah.
I will continue. So I want should I go backwards? Sergey, should I
Sergey,
go?
do you hear everything? We lost Sergey.
Yeah. So should I go backwards?
Wait for them to.
I still have problems. I have sounds, strange sounds.
Strange noise.
Robert, when you switch off your microphone, do you still have problems with sound?
Yes, when I switch off my
Then we don't hear you.
It's important that he hears you.
Danko,
it sort of doubled this sound and mixed somehow. Even if I switch off my microphone, I have problems with the sound. We can check again. If I switch off, please say something.
can you hear me now?
It is damaged. It is overlapping of two sounds. Like echo or something.
I hear the echo.
We lost only Sergey.
Sorry?
I look at the list of participants and Sergey disappeared.
So let us wait, because he is the host, Amnon.
Yeah, they switched hosts now.
I think, yeah, because they want Juzar to take over.
This damage appears suddenly. You start with a perfect sound, and then at certain point of your presentation, sounds start to double.
Not here.
So I don't know, should I go backwards? Should I go?
No, it's doubled. I mean,
Alexei, you are at the PCS?
Or it's your problem because I can hear Amnon's very well and your sound is not good.
I can hear her.
Yes, I will go check what's happening with Sergey because I don't have any issues. For me, the sound and the video is perfect.
Yeah, so it's only Sergey's problem, probably. Is he in the office?
Yeah, so I'll go and check him now.
Okay.
Oh.
In the meantime, it's nice to see you, everybody.
Yeah. Danko, how are things?
So far, so good. For me, at least, and my family, but I couldn't say the same for the many people in this country. More and more people are getting ill, but it's like that everywhere in the world. So I suppose it's supposed to be.
You stay at home all the time?
No, I'm at work now, but I'm alone in the office, and I bought a small car instead of bike to come to work, not to use public transportation. So I'm practically isolated from most of people.
So are you, Amnon?
I'm okay.
No, I mean, you are also quite isolated.
I like it. I work in my home and everything is fine. Work is very effective.
That is correct.
To me, it's less effective at home.
Is it because you have children around?
Yeah, well, you know.
I also like company. I also cannot say that I like it.
Okay, hello. Ora, I'm sorry.
The
problem was actually with my
hello.
With my computer. So
sorry, everyone. I just had to. Sorry, now I'm back in control of this, and maybe I can make Sergey the host again. I'm sorry for all these interruptions. Good. So Sergey, please, maybe I can make you the host once again, if you are online.
So should I go back on my slides?
Yes, Ora, please. I mean, sorry, because there were these interruptions in between.
Okay, so I'll try to start again from the explanation why the Aharonov-Casher effect is not a bare phase.
Please, if you could. Thank you so much.
So what I wanted there, I don't know if you heard me on this slide or not, but I'll say it again. What I wanted to say here is that we are moving the electron in the plane, first along the x-axis and then along the y-axis. And we look at what happens to the spins. So when we move along the x-axis, the electron rotates around this, not the electron, the spin rotates around this axis. And when we move along the y-axis, the spin rotates along this axis. And therefore, each of these partial rotations of the spin each of these is in the plane, in the xy plane. However, when we ask ourselves what is the total rotation when we went from this point to this point, we find that because the non-abelian character of the Aharonov-Casher phase, the electron in fact rotated around that axis, which is not in the xy plane, but it went out of it by a certain angle determined by all the parameters of this problem. And the Aharonov-Bohm effect, or the Aharonov-Bohm phase, is quite different than the simple sum that we had with the Aharonov-Bohm magnetic phase. When we do a better calculation, a full calculation, like going on a ring, the ring is shown here, then we find that there are two limits to this problem. We can ask ourselves, and the two limits are determined by the ratio of two frequencies. One of the spin orbit induced Larmor frequency. Let me explain this lengthy title. Since the spin orbit interaction can be presented with a pseudo-magnetic field, it has a pseudo-Larmor frequency, which is denoted here by W sub spin orbit, SO. And that is the frequency of rotation, of the kinetic rotation around the ring. So if W sub SO is much larger than this rotation, the electrons always follows the axis of the spin orbit interaction. In that case, the tilting angle that I discussed before will be pi over 2, namely the electron will stay in the plane. And the Berry phase for this motion is pi over 2 as it should. However, if this criterion is not, this is called adiabatic limit, by the way. If this criterion is not fulfilled, then the electron, the axis of the spin rotation will be tilted out of the plane. And when one does the entire full calculation, one finds that the entire rotation angle consists of what is called in the literature a dynamic phase, and another thing which is called Aharonov-Ananden-Berry phase. In other words, the axis of rotation is tilted with respect to the z-axis, to the axis of the electric field forming the spin orbit coupling. This angle is called theta, and the total angle, the total Aharonov-Casher phase, consists of two parts. One is called dynamic phase. I will not go into it now. And the other is some generalization of the Berry phase, and the generalization was accomplished by, again, by Aharonov in collaboration with an Indian guy named Anandan. So you see that we also have the AA effect as well. But you see that if we measure the Aharonov-Casher phase, we will not know what is the tilting angle that the spin orbit interaction causes the electron or the spin of the electron to have, because we'll have this complicated formula which holds only for a perfect ring. So in each system, you have to do the entire calculation from fresh. So the physical quantity here is in fact the tilting angle and not the Aharonov-Casher phase. Or in other words, the Aharonov-Casher phase is not a Berry phase. So you will not be able to measure it. So these are the answer to the two questions I posed before, namely, is Aharonov-Casher phase a Berry phase? The answer is no. And is there an AA effect? Oh, effect. The answer is yes. Okay.
or I'm sorry, there's a question by Sung Jong Woo. Please,
Yes.
Sung Jong, unmute yourself.
Yeah, I'm listening.
You have to unmute yourself, Sung Jong. Yeah.
When you calculate the Aharonov-Casher phase, do you consider the effective magnetic field due to the motion of the spin?
I'm coming to this. It depends what do you mean to see the effective magnetic field. As I say,
Before you said that, I mean the speed of recoupling of the like moving charge. Normally, I mean you said that there is effective magnetic field.
yes.
So in this case, is it also considered? Is it the way how to calculate the Aharonov-Casher phase?
I'm coming to the measurements. Coming. The answer to your question hopefully will be in the following. If not, then please ask me again.
Okay.
Okay, so just to summarize what we have done so far, we have the AB effect. This guy here is Bohm. We have the Aharonov-Casher effect. This guy is Casher, also from Tel Aviv University. And this guy is Ananden, that's the Aharonov-Ananden geometric phase. And here you see Aharonov himself getting some medal from Obama. Okay, and just to make sure, the Aharonov-Ananden geometric phase is a part of the Aharonov-Casher phase, not the entire Aharonov-Casher. So back to my plane rod, we have talked about the spin-orbit coupling. We mentioned the topological insulators, which are based on spin-orbit coupled systems, and we discussed the Aharonov-Casher phase. And now I'm coming to the answer to that question in a way, namely the rather futile attempts to measure the Aharonov-Casher phase in condensed matter interferometers. And then at the end, finally, I will come to, in 2 minutes, to tell you what we contributed to this. Okay, so when the entire story with the spin-orbit interaction became fashionable, then of course people wanted to measure it like it was measured with the magnetic field. So what should we do? We have to take a ring. Here is a ring made of indium aluminum. This is again some two-dimensional electron guide. There is the gate electron, which before I call the plunge electrode. There is the two-dimensional electron guide, and we want to measure the conductance. I mean, the material here are known to have a spin-orbit interaction, and we want to see whether we will see in the conductance some effect of the spin-orbit interaction. And the answer, unfortunately, is no. There will be no spin effect in a two-terminal measurement. I remind you, two terminal is when you have a source and a drain and no third terminal. And there will be no spin effect if you do not break time reversal symmetry. And as I mentioned, the spin-orbit interaction by itself does not break time reversal. So this nice proposal by a Japanese group didn't work. So what people did was to apply a magnetic field and see what happens when you have magnetic field. They really mean either the Aharonov-Bohm effect or the Zeeman interaction. And then try to measure what is going on. And then people actually misinterpreted the data. Because of this problem that the spin-orbit interaction phase is not abelian, and it cannot be connected simply, that there were some problems in analyzing the experiments. And what they did basically was to analyze such an experiment based on the perfect circular ring that is derived in the absence of the Zeeman field, of the Zeeman magnetic field. And then what they got was simply not the right effect. There were other, a little better, somewhat better experiments again, but they are again in the presence of magnetic field. What you see here is again measurements of this kind, and you see that they show various oscillation as function of the gate voltage. I remind you the gate voltage monitors the electron density in the ring, and the actual magnetic field, the one that breaks time reversal symmetry. But the situation was not satisfactory because the Aharonov-Casher phase was not measured. So now, at the end of the day, I am coming to our suggestion. And our suggestion is that since you have to break time reversal symmetry, maybe you should measure some other quantity. Okay. So let me summarize till this point. How do I do with time? I don't have any.
Well, there was a glitch because of apparently my computer, my desktop. I think how much more time do you need? 10 minutes, is that fine?
Yeah, 10 minutes I'll finish.
Perfect. Just go.
Very good. So let me summarize what I did so far. And I said, while Aharonov-Bohm conductance oscillations allow for experimental detection of the Aharonov-Casher phase, the separate detection of the Berry phase there is still elusive. Namely, when you combine together spin-orbit interaction and magnetic field, you can observe to some extent the Aharonov-Casher phase, but you don't observe the Berry phase. So we need to measure something else, which is not the charge current. And now I come to our proposal. I'll tell later who are our. And it is to measure spin-dependent transport in an interference tunnel junction subjected to both the electric field, which induced the spin-orbit interaction, to the Aharonov-Bohm magnetic flux to distinguish in the conductance the interference pattern, and to a Zeeman field to break time reversal symmetry of the junction. So all three effects should combine together. And what is a tunnel junction? I'll first show you my version of a tunnel junction. So we have some source of electrons. Then we have a junction. This is the junction. I'll come to it in a minute. And we have a drain. And this junction is made of a ring. This ring is a little bit triangular, but it doesn't matter. There is still interference between going along this path and along this path. And along the upper path, we put also a quantum dot. Now there is a electric field normal to the plane of the picture, and also magnetic field normal to the plane of the picture, which means that we have the Aharonov-Bohm phase or the Aharonov-Bohm flux through this junction. And we also can modulate the spin-orbit interaction by modulating the electric field. So this is the system that we want to study. And we studied it theoretically. Let me just remind you that a magnetic field has two effects on the motion of electrons. You have the Aharonov-Bohm effect, which is the coupling between the magnetic field and the orbital motion, actually the momentum. And there is also the Zeeman interaction where the magnetic field is coupled to the spin. And the two of them have different effects. So why is Zeeman interaction needed? Because of the following. Although the tunneling amplitude in the presence of spin-orbit interaction allows you to flip the spin during the tunneling. I mean, you can you tunnel from one point to the other, you can keep the spin or you can flip the spin. The tunneling probability just by spin-orbit interaction is independent of the spin-orbit interaction. This has to do with the time reversal symmetry of this interaction, and as a result, this tunneling amplitude is a unitary matrix, but that's technical. Now, the Rashba interaction is time reversal symmetric. The tunneling amplitude is a unitary matrix. That's what I say. And the Zeeman interaction that also enters through the tunneling mechanism, it breaks the time reversal symmetry, and the tunneling amplitude ceases to be a unitary matrix, and therefore the spin-orbit interaction will affect the tunneling. So that's the essence of the thing. Okay, so what is a tunnel junction? A tunnel junction, as I said many times through this talk, you have a source of electron, you have a junction, this is the red part, and you have a drain. Another way that experimentalists would like to present it, you have a quantum dot that the tunnel coupled to drain and source by two tunnel junctions. And you have a gate, and as I said, the gate can change the properties of the electrons, the density of the electrons in the junction. For a theorist like me, a tunnel junction is some junction, which is spin orbit active. It's a weak link, if you wish, and it is coupled to two Fermi distribution on the left and on the right. And the two Fermi distribution is determined by the temperature of the reservoir of the source and the chemical potential there. And the same for the right side. And this is the Fermi distribution. So that's the way we see a tunnel junction. Okay, so now we have to do some transport calculations. So let me tell you what we calculate, because it's on its face, it's very, very simple. You have an Hamiltonian, and the Hamiltonian consists of three parts. You have the Hamiltonian of the left lead, which I just said it's that, let's take it as simple as a free electron gas. You have the Hamiltonian of the right lead, and you have the Hamiltonian of the tunnel junction. That's what you have in the Hamiltonian. And what do you want to calculate? You want to calculate the rate of change of the number of electrons, let's say in the left reservoir, in the left lead, which is that the time derivative of the number. These are the creation and the annihilation operators of the electron, and the angular brackets means the quantum average. So this is the current. And if you will go and calculate the change of number in the right lead, you will find the same result, because current is conserved. The charge current is conserved. However, you can calculate something more, and the something more is the rate by which the magnetization is changing. And what you find, okay, let's first define it. So let's say, what is the magnetization in the left lead? You have actually the magnetization operator with a quantum average, and the magnetization operator is the Pauli matrix between two operators, and you take the quantum average of this quantity. So you see that the magnetization is a vector, because you can put here any of the three Pauli matrices. So first you have three. If you look at currents and you look and you ask yourself what is the rate of change of the magnetization, there are three of them, along X, along Y, along Z, because of the three Pauli matrices. But the important thing is that the magnetization current, or the spin current, if you wish, is not conserved. And why it is not conserved? Because you have spin-orbit interaction, and spin-orbit interaction changes the direction of the spin. So the spin currents are not conserved. So the spin from the left will not, the spin current from the left is not equal to the spin current of the right. Okay, so that's what we want to calculate. And then you go and calculate it, and you work, you do something which is called Keldysh technique, and which I don't have any slide about. At the end of the day, you find an expression for the charge current. And how does this expression look like? It's an integral over all the frequencies of the Fermi distribution of the right minus the Fermi distribution in the left. If you wish, this in linear response gives you the voltage times the transmission. That's it is called the Landauer formula, and it's very, very simple. However, in our case, the transmission is a 2x2 matrix. And why it is a 2x2 matrix? Because you can ask what is the transmission that spin up from right goes to spin up from left, or spin up from right goes to spin down from left, and all the other two. So you have a matrix. And when you want to calculate the current, you have to sum over all directions. So it's a trace in spin space. Okay, and then we went, I'll tell you who are we in a minute. And we found the result, and the result turned out to be the following. First, we see the cosine, and that's the result for the current. First, we see the cosine of the flux, the magnetic flux, in terms of the flux quantum. This is from the Aharonov-Bohm oscillation. And this is multiplied by the cosine of the Aharonov-Casher phase. And then there is another contribution that is odd in the Aharonov-Bohm flux, and it's multiplied by the Zeeman. I write it in a way, although it's the same field that makes the flux And the Zeeman interaction, the coefficients are different, so I write it in this way. And why do I write it this way? To emphasize that the entire current or the entire conductance is even in the magnetic field. You see, phi is the magnetic flux, and cosine phi is, of course, even in the magnetic field. Sine phi is, of course, odd, but then it is multiplied by the Zeeman term. So at the end of the day, you get an even term. And actually, from such a calculation, you can deduce the cosine of the Aharonov-Casher phase. But still, you don't know the tilting angle of the magnetic field or the Berry phase connected with spin orbit interaction. To this end, said we, you have to calculate the spin current. And as I said, the spin current turns out to be very much like the charge current, except that in the trace of the transmission, you have to put the Pauli matrix vector, because the spin current, as we saw, is a vector. And the spin current from the left, which is specified by this transmission left, is not equal to the spin current from the right. There are two different things, two different interference patterns, which depends on the geometry and from which you can deduce all the phases that I discussed before. So this basically what I wanted to tell you about our work. But if you are more interested, then before I do my conclusion, let me tell you that this is all published in the first volume of Physical Review Research, and it's by Amnon Aharoni, that you know, and me. So these are we. And let me just present my conclusion. So due to time reversal symmetry of the spin orbit coupling, measuring interference by longitudinal conductance yields the Aharonov-Casher phase, which is not a Berry phase, what people wanted to measure. And the detection of the spin tilting angle requires breaking of time reversal symmetry, namely the Zeeman magnetic field. And the tilting angle of the spin can be detected by measuring the spin current. And I just put a little figure here to tell you how one measures spin current. And in fact, one does not measure spin current, one measures spin accumulation. And this can be done by the magneto-optical Kerr effect, which is the rotation of the polarization direction of the laser beam because of the amount of spin that is accumulated on the sample. And I think by this, I thank you for your attention.
Okay, thank you very much, Ora. Thanks for this very nice and interesting colloquium talk. I'm very sorry for the glitches which happened on the way, and I think we should now give some applause and thank you. And now the talk is open for questions, discussions, comments, etc. And I see that already some participants unmuted themselves, so I expect, yeah. Who wants to start?
I may ask a question. So it's important in this setup what you suggested to put magnetic field to break time reversal symmetry and make it observable. I wonder if instead of magnetic field you will put time dependent electric field, would it, which also supposedly remove time reversal symmetry, would it be possible to make such a version of experiment?
I think that you would like to have some oscillatory time dependence. So, and then you can ask yourself, what is the spin accumulation or the spin tilting angle after a period of the let's say electric field, yeah, or something. So I think it is possible, but at this stage we didn't do this calculation because you see the way we did it is anytime we said something more is something else is missing, we added something more to the setup until it became so complicated.
Yeah, it's complicated maybe, but who knows what is easier for experiment? I mean,
yeah.
And Robert, if I understand correctly, you want to have a time periodic electrical field in order to emulate a magnetic field. Is that your point?
No.
Or
I think if you have
symmetry.
Yes, if Hamiltonian is time dependent, you have no time reversal symmetry in the system in general.
No, you can have if the
it depends,
is universal.
But also you can ruin it, I mean, so to speak.
But you can break
time dependence. Time dependence can be not time reversal. I mean,
right.
Yeah, and then you can remove magnetic field and ask the question: would it by itself create this effect?
Yes, yeah. I would say that yes, but one has to. I think that yes, but I cannot tell you 100%.
Yeah, of course, but in principle.
In principle, it should.
We have also found that you can polarize the reservoirs, the leads, and that also breaks time reversal in another way. Yeah. But we have not addressed that question in the context, in the present context yet.
Yes.
Because the way we see the leads is that some external agent is keeping the leads at equilibrium and don't allow anything there.
Yeah, but we could have kept it at a constant magnetization and asked what that does, and we have just published a paper doing that for a single link. We could recalculate it for the triangle and see what happens.
That is correct. Yeah.
Robert, you had another question? Did I catch?
No, I am fully satisfied. It's very interesting presentation, Ora. It's nicely made. Thank you very much.
Thank you very much.
Other questions and comments, please.
If I may ask a question, I'm actually surprised how many different types of phases one can expect digging deeper inside the problem. For example, I've heard of geometrical topological phase, which is very phase, then dynamical phase. Now we have this Aharonov-Casher phase, which is who knows what in between. Now, you said that Berry phase is essentially a fractional part of flux.
Yes.
Do you really expect that it will, because Berry phase is defined in a very abstract way on this sphere with this tripod going along closed loop, do you really expect that it would not appear as a Berry phase unless you have magnetic field and fractional part of the flux?
Look, it appears, but it does not appear in a physical measurable quantity. The reason I say a partial magnetic flux is that you define the Berry phase only up to 2 pi. Therefore, you can, of course, increase the magnetic field monotonically, and it will increase, but you look at the fraction within 2 pi.
So always magnetic field. But if you, for example, make some sort of artificial lattice in which you arrange atoms along the half loop and then make atoms jump from each side to side, like in tight binding approximation, and emulate effect of Lorentz force. It means you emulate some sort of artificial magnetic field. Mm-hmm. Can this field, this effective field, coupled to your spin of electron moves that way and give you effective magnetic field, giving rise to the effect that you predicted?
I'm not sure that I understand you properly, but the point is that there is indeed a pseudo-magnetic field, but you have a different magnetic field for each spin direction. So any quantity like the conductance, where you sum over the 2 spin directions, this will disappear. You see what I say? Because one spin direction reacts in one direction and the other one will react in the opposite direction. So when you sum over them, it disappears. So you need to look at some quantity that distinguishes the spin directions. And these are spin currents in a tunnel junction.
Okay, I meant something different. You take one electron and force it by arranging your lattice of atoms to move along the loop or half loop. It means it moves as if some magnetic field, some Lorentz force acts on it. So this artificial magnetic field, pseudo field, would it give you effect? Would it couple to the spin of this particular one electron and give you this effect that you predicted?
But the one electron is in which, if it is in a definite spin space, you mean?
Yeah.
But then you broke time reversal symmetry.
Yeah.
Then the answer is yes. If you know what is the spin direction of that electron, then you broke time. I think you broke time reversal symmetry.
So the answer is yes, practically.
The answer is if you break time reversal symmetry, then you can measure the spin.
Okay, I need to think about it. Thanks.
Okay, more questions, comments, please. Amnon, you unmuted yourself. Do you have a comment?
I wrote the paper.
Right. Is not answering my question. So apparently you don't have a, well, you did, right. Okay. Once again, a call into the round, because it's a bit late already, I guess. Well, at least here in Korea, while in Europe and Israel, the sun is probably just coming out, it seems.
Yeah.
Well, if there are no more questions, then I suggest that we end this colloquium talk here. I don't know, Ora, whether there was any agreement with Juzar, whether there will be any after colloquium discussions or whether you have other plans.
No, it didn't mention.
I would say, I don't know.
We have a Zoom meeting in 40 minutes.
What did you say, Amnon?
I said to Ora that she and I have another meeting in 40 minutes.
Okay, we will therefore probably just end the whole the event here. And I want to thank very much again to Ora and to the whole ASG team. And I'm looking very much forward to see you here again. So thank you, Ora. Bravo.
Bye-bye. Bye-bye, everybody. Bye-bye.
Have a nice day back in Europe and see you soon. Thank you.
Bye-bye.
Goodbye, everybody.